Okay. What do we have? We have first the dimerization reaction, where the dimer is written A subscript 2. This will occur with some given equilibrium constant, dissociation constant. If you assume this dimerization at equilibrium, we can write the equilibrium ratio of the reactant and products as the concentration of A square over the concentration of the associated compound is equal to the dissociation constant of the reaction. This is one reaction. Then we have the reaction for binding of the dimer on the promoter. With a dissociation constant K2, assumed at equilibrium, means that the product of A2 times the promoter concentration over the concentration of the bound promoter is equal to the reaction dissociation constant. What do we have also? We still have the promoter conservation rule. That is, exactly as before, the promoter is either free or bound, so that the sum of these free and bound promoter concentration is constant, is the total promoter concentration in the cell, the conservation. The quasi-equilibrium, quasi-static assumption, the conservation rule. What do we want? We want to obtain the differential equation for the rate of the gene production, the mRNA production, which will be given by which will be dependent. Here it's changed nothing from before. It will be dependent on the binding of the dimer on the promoter, and so the mRNA concentration will be dependent. The rate of mRNA concentration production will be dependent on the concentration of the bound promoter. And have the degradation, if you want to include the degradation test. So, as before, what we want to obtain is an expression for the bound promoter concentration as a function of the transcription factor monomer concentration. Okay? We want to make use of our quasi-static assumption and conservation rule to find this function, in this case where it is the dimer that binds. I erase this to have some room. And we will combine all these equations together, make use of all the knowledge to find an expression for the bound promoter concentration. First, we use the first equilibrium constant. And to make usage of this knowledge in the second equilibrium relation that we have. And for this, we see here in the second equilibrium equation, we have the concentration of the dimer. And this concentration of the dimer, we can express it as a function of the transcription factor A concentration, making use of the first equilibrium constant. So we can make use of the first expression to replace dimer concentration with a relation depending on the A monomer transcription factor concentration. So, making use of 1 into 2, we can write, I write again I write again 2, and now we make use of 1 to replace A2 by what is A2 depending on A? It is A squared over K1. So this, by changing where is the K1 dissociation constant, we can rewrite this as A squared times K2. And we have all the dissociation constants only on one side. Here is making use of the first equilibrium expression into the second one. Okay, so now we are almost done. We have the concentration that we are looking in a relation where there is variable, the DNA concentration, the transcription factor concentration, but there is this unknown free promoter concentration. To remove it, we make use now on the conservation rule. Now it is exactly the same algebra as in the previous very simple case of the monomer binding. We wrote the whole expression. So let us use now conservation rule to express the free DNA concentration. This is DNA dot minus A2 DNA. And here is an equation for the quantity we are looking, bound promoter concentration, where you have only the variable that participates and the parameters, the dissociation constant and the conserved quantity. So these we can solve. I will erase what we don't need anymore. Simple algebra to solve for A2 DNA. Let us do all the steps. I multiply left and right by concentration of A2 DNA. Equal, so the denominator was removed. no more fraction. We have the quantity that we are looking on both sides of the equation. Let us move these negative part on the left. So by A2 DNA K1 K2, this one, and this came to the left, then it is plus factor with A2 equal what remains on the right. Okay, A2 DNA can be factorized. I really give you all the steps of the algebra. So that you have all the details of those small computations that you should be able to do, or you should learn to do for this simple algebra. And finally, since we have here now only the variable that we are the quantity that we are looking, we can divide left and right by this part, and we have the quantity of interest, and on the right we have DNA dot equal A2 over K1 K2 plus A square. Here is multiply. This is our concentration of bound promoter by the dimer as a function of the free transcription factor monomer. What we note is this square exponent on the in the fraction. So again, the final result for the gene activation is what we expected, that the gene activation depends on this fraction with the square of the transcription factor concentration. And this is no longer the hyperbolic function, but it is a function with a square. This function with a square is called the Hill function of second order. Second order because you have a square. It is a nonlinear function.